Welcome back. In this video, we continue our study of chapter 4 and we move to section 4.5 about separable spaces. What is a separable space? A topological space is said to be separable if it contains a countable dense subset. So, for example, Rn is separable. Why? Because it can Q to the n is a dense set which is countable. And we proved in exercise 1 of chapter 1 that a totally bounded metric space is separable. So a compact metric space is separable. So separability is a desirable property for a space to have, but not all spaces possess this property. And note that this property is a topological, what we call a topological property. So it's a property conserved by homeomorphism. So if two spaces are homeomorphic, then they are separable. They are both separable or both not separable. So in particular, two isomorphic norm spaces are either both separable or both not separable. So let us give, as usual, some examples. The familiar space C01 of all continuous functions from 0,1 into R equipped with the uniform norm is separable. This is actually a consequence of the Weierstrass approximation theorem, because given a continuous function, we can approximate it on the compact set 0,1 by a sequence of polynomials. But a polynomial with real coefficients can be approximated uniformly with a polynomial with rational coefficients. Okay? So therefore, we can approximate uniformly a continuous function with a polynomial with rational coefficients. Okay, so the set of polynomials with rational coefficients is dense in C01. But the set of polynomials with rational coefficients is countable, as you may prove, because essentially Q is countable. Okay, so therefore C01 is separable. Another example, the sequence space L to the P for P finite is separable, and here's the proof. Okay, so consider the set capital A of all sequences of the forms R1, etc., Rn, where each Rk is rational. So these sequences are 0 starting from a certain rank. Okay, so if you consider the set of all such sequences, I claim that this set is countable and dense. Now, it's not difficult to see that this set is countable because essentially Q is countable. So we have finitely many rational coordinates, if you like. So it's not difficult to prove that A is countable. Now we prove that A is dense. So I go back to the definition. Take an arbitrary element x in LP, so x is a sequence, and consider an arbitrary positive number epsilon. I need to prove that there exists an element A in capital A whose distance to x is less than epsilon. The distance in the norm LP, of course. So if x is in LP, what does it mean? It means that the series of a general term xk to the p is convergent. And therefore, the remainder of a convergent sequence tends to 0, and therefore can be made less than any positive number I like. So there exists an integer m starting from which the remainder starting from m plus 1 is less than epsilon p over 2. And now, so this set is the what happens after m plus 1. But if now k is between 1 and m, since we can approximate real numbers by rational numbers, for each k between 1 and m, I can pick a rational number, rk, whose distance in r is less than epsilon over 2m to the power 1 over p. And now I take r to be the sequence of coordinates r1, etc., rm, and 0 starting from m plus 1. Now, when you raise this to the power p, we get epsilon p over 2m. And when you do the summation from 1 to m, you'll get epsilon p over 2. And then when you do the summation from m plus 1 to infinity, you'll get epsilon p over 2. So therefore, the distance between r and x in the p norm to the power p is less than epsilon p. Therefore, the distance between x and r in the norm P is less or equal than epsilon. And this proves that the set capital A, so R is in capital A. So no matter how epsilon is small, we can find an element in capital A arbitrarily close to x. So this proves the density of capital A. Okay, now a counterexample. L infinity is not separable. Okay? So consider a countable set capital A consisting of points A1, A2. So each AK is a sequence actually. So this is actually a set of sequences. Now we'll show that this set cannot be dense. Okay? So no matter what countable set I take, cannot be dense. So there's no countable dense set. So define a new sequence B with coordinates BK as follows. So BK, this is a real number, BK is just the kth coordinate of AK plus 1 if it's less or equal than 1 and 0 otherwise. Okay, this is a trick, but why did we take this? So first of all, BK is less or equal than 2 because it's either 0 or AKK plus 1, and this happens if each term is an absolute value is less than 1, so BK is less than 2, and therefore B is an element in L infinity. This is the first observation. Second observation, let us evaluate the distance between this sequence B and an element, a sequence A to the K. Now, by definition, this is the supremum of all the coordinates. So it's in particular for any K, in particular for the kth coordinate. So the infinity norm of B minus AK is bigger or equal than the distance between their K coordinates. So this distance is bigger or equal than BK minus AKK. And this is at least 1. Why? Because there are two cases. If AKK is bigger than 1, then this is 0, and therefore I get AKK, which is strictly bigger than 1. So bigger than 1. If AKK is less or equal than 1, then the BK is AKK plus 1, so the distance is 1, so it's bigger or equal than 1. Therefore, but this is true for every K. Therefore, when you take the infimum over K, we see that the distance between B and A is bigger or equal than 1. So in particular, B cannot belong to the closure of A. And therefore, A bar cannot be equal to L infinity. So we found an element B, which is an L infinity, but not an A bar. Okay. So L infinity is not separable. Okay, so that's the fundamental example. Okay, so now let us establish some properties of separable metric spaces. First result, a metric space is separable if and only if it has a countable basis. Okay, two implications. Suppose first that E is separable. The metric space is separable. And therefore there exists a countable dense set capital A that I can enumerate as A1, A2, etc. Now consider the collection of all open balls of center AN and radius 1 over M. Now it's easy to check that this collection of balls is a basis for the metric topology. Okay? You should be able to write the details by yourself. Okay, so go back to the definition of basis of topology. This means that, what do you want to prove? You have to prove that any open set in the metric space C, and for any X in this open set, we can find an element in this collection containing X and contained in O. So this is the meaning of a basis. Okay, now conversely, suppose that E has a countable basis that I call B capital B sub n. Okay. Now, for each n, choose an element in this in AN and BN. Yeah. So because so each element is not empty. Okay. And now we have form a new set by selecting these elements. We get a new set capital A. And it's easy to see that this set obtained by choosing one element in each basis element This is dense, actually. Okay? Why? Because every non-empty set contains some Bn, and therefore it meets A. Very easy. Okay, so as a corollary, a subset of a separable metric space is itself separable. There are at least two proofs of this, but now since we established the equivalence between separability and having a countable basis, it's easy to prove this. So consider a separable metric space E and consider a subset Y of E. We know from the previous proposition that E has a countable basis Bn. Now when we intersect Bn with Y, we get actually a basis for the topology of Y by the definition of the subspace topology. And this is now countable. So it's very easy. Okay, so you may pause the video at this point if you are tired before we continue, but I will not stop. So now, in the context of norm spaces and weak topology, you have, so I'll present three results. I will just prove the first one. So the first result is the following. If the dual of a normal space is separable, then the space is separable. Okay, but the converse is not true. And you should be able to give a counterexample, actually. So we are saying that if E star is separable, then E is separable, but the converse is not true. Okay, so this is an illustration, actually, of the use of the geometric form of the Banach theorem. So since E star is separable, then we have, by definition, a countable dense subset that I can enumerate, F1, F2, etc. Now, by definition, so each Fn is an element of E star, so it has a norm. And the norm, by definition, is the supremum of Fn over the closed unit ball of E. Now, by a property of the supremum, when I take something smaller, it's not an upper bound anymore. So therefore, if you take epsilon to be the norm of Fn over 2, then you will find an element in the ball which is not bounded by Fn minus epsilon. So it's bigger or equal than 1/2 times the norm of Fn. Okay, so we take epsilon. We already used this characterization several times. So you take epsilon equal norm of Fn over 2. Okay, so therefore we have this inequality that I refer to. Now, let us denote by L sub 0 the set of all finite linear combinations of x1, x2, etc. This sequence that we just constructed, but with rational coefficients. What does this mean? This is otherwise stated L0 is the vector space over Q generated by xn. Okay, and now if I consider the set of all finite linear combinations of x1, x2, xn with real coefficients, I call the set L. So this is the span. So if you like, L0 is the span over Q, and L is the span over R. Now, it's easy to prove that L sub 0 is countable, essentially because Q is countable. You may write the proof if you like, because you have finitely many coefficients within Q. Okay, and since Q is dense in R, it's easy to prove that L0 is dense in L. Okay, because Q is dense in R, because you can approximate any real number by a rational number. Now, if you prove that L is dense in E, then L0 would be dense in E, okay? Because just write it. Okay? So if we can approximate an element in E by an element in L, and you can approximate an element in L by an element in L0, then we can approximate an element in E by an element in L0. Okay. So now we have to prove that L is dense, and for this we use a corollary of the Banach theorem, corollary 2.4. How do you prove that a set is dense? We take an element in the dual of E that vanishes on L, and we prove that it vanishes on E. Okay? This is the strategy. Okay, so pick a positive number epsilon. Now, By density of the set F1, F2, we can choose an index or an element in the set whose distance to F is less or equal than epsilon. This is by definition of density. Now, according to 1, since F by definition vanishes on L, then F vanishes at Xm. Okay? Therefore, inequality 1 tells me that 1/2 times the norm of Fm is less than the value of Fm at Xm. It's the real number. So when I subtract Fm of Xm, I get the same thing because F vanishes at L. So, and now by the fundamental operator inequality, this is less than the norm of F minus Fm times the norm of Xm. But Xm is in the unit ball, so it's less or equal than 1. Therefore, 1/2 Fm is less or equal than epsilon. And now by the triangle inequality, the norm of F is less or equal than the norm of F minus Fm plus the norm of Fm. The first term is less than epsilon, and the second term is less than 2 epsilon. Therefore, norm of F is less than 3 epsilon. And since epsilon was arbitrary, this means that F is 0. So this concludes the proof of this first result. So, but now you should be able to give a counterexample for the converse. So give an example of a separable space whose dual is not separable. I may ask you this question in the exam. Okay, so as a corollary, we can prove that the following conditions are equivalent if you have a Banach space. So E is reflexive and separable if and only if E star is reflexive and separable. So once again, take a paper and a pen and try to prove that on your own, because this could be a typical examination question. Okay, so now I will just present 2 results without proof because the proof is lengthy, and so I don't want to burden you with lengthy proofs. So I'll just state the proofs, the theorems. So if E is normal space, then the following conditions are equivalent. E is separable. The closed unit ball of the dual is metrizable in the weak star topology. And third condition, every bounded subset of E star is metrizable in the weak star topology. Okay. The proof is in the lecture notes. So if you are really interested, you can just read it. Okay. Now, don't worry, I will not ask you about something that I didn't give in the lectures. But okay, and we have a dual theorem of this. E star is separable if and only if the closed unit ball of E is metrizable in the weak topology, and it's equivalent to saying that every bounded subset of E is metrizable in the weak topology. Okay. Now, you should not be confused because we proved that if E is infinite dimensional, then both the weak topology and the weak star topology are not metrizable on the whole space. But when we restrict them on a bounded subset of E, then they could be metrizable. And this happens if and only if. So in the case of the first theorem, a bounded subset of E star can be metrizable in the weak star topology. And this happens if and only if E is separable. And we have a dual statement. So a bounded subset of E is metrizable in the weak topology if and only if the dual is separable. Okay, so don't confuse the 2 conditions. Okay. Okay, and now having stated this, we can easily prove that a remark that we said in a previous video, that in a reflexive space, the closed unit ball is not only compact, weakly compact, but is weakly sequentially compact. Okay, so this means that in a reflexive space, every bounded sequence has a weakly convergent subsequence, and this is a very practical result in analysis. Okay, so this actually this follows from the previous 2 results. So why the unit ball of a reflexive space is weakly sequentially compact? Okay, not sequentially compact, weakly sequentially compact. So consider a sequence in the closed unit ball Xn, and consider the span, the smallest subspace containing x1, x2, or the set of all linear combinations of x1, x2. So call it F0. And consider the closure of this span. Okay. Now, F as a closed subspace of a reflexive space is itself reflexive. Okay, and it's easy to prove that it's also separable. Why? Because if you take the span over Q, then this is a dense countable set of F. Okay, though we already observed this argument. So F is reflexive and separable. And according to a previous result that you didn't prove, that then F star is separable. But according to the first theorem, the second theorem actually, if F star is separable, then the closed unit ball of F is metrizable. Okay, but since F is reflexive, this ball is weakly compact. Okay, so it's metrizable and compact in the weak topology. Therefore, it is sequentially compact in the weak topology, and therefore Xn has a weakly convergent subsequence. So please add here is weakly sequentially compact. Okay, so this concludes the video and section 4.5. Thank you for your attention and see you next time.